Hi, everyone, and welcome back. Today, we have a very special guest and a personal friend of mine, Jason Costello. Jason is an extremely competent data scientist, but he's also an extremely competent data engineer. And he is one of the people who first introduced me to the world of deploying data science into the real world. So he's been a very useful mentor with a great fountain of knowledge that he's more than happy to share with people. And so I wanted to start covering an important issue, which is the deployment of data science models into the real world. And particularly, I have this thesis that a lot of data science, when people talk about it, are sort of the genesis of the term data science and the role data science comes from the fact that we've had a proliferation of software that collects a massive amount of data, and traditional statistical roles were not sufficient in their skill set to handle those and handle the business concerns and the application concerns around that software generated data. And so it required a new skill set, and that new skill set started to be called data science or data science for a data scientist. Although admittedly anyone can name a title anything these days. And so there's that. But Jason has a massive amount of knowledge on this issue about actually taking models and putting them into the real world, making them embedded into software and machines and moving that along. So I think we are very lucky to have someone who's both skilled from a data analysis perspective and from a software engineering and deployment perspective. That's a unique skill set. Jason has been called a unicorn by some very successful people. And today we have a unicorn prancing about on our podcast. So Jason, welcome. Thanks so much for coming on today.
Thanks for having me, Glenn.
Yeah. We have a lot to unpack because basically I would like us to do a gentle introduction to the sort of the challenges of putting data science in production, data science versus software. There's quite a bit. Actually, that reminds me, we had a Q&A yesterday, and someone was asking me about agile data science. And I was a little bit circumspect on whether or not agile is the right, development paradigm for data science. But I also then wish you were there because you could have given a better answer than I did. But yeah, where should we start? First of all, maybe I think it would be helpful to establish your machine learning, data science, and data analysis credentials, because you do have a PhD on effectively anomaly detection, and like the best of us, you did it working on, I believe, engine anomalies. Is that right? Yeah,
that's right. Yeah. So I have a doctorate from the University of Strathclyde in Glasgow. So I started off my work in a really academic environment. We were, as you were saying, working on applying machine learning to condition monitoring for rotating machinery in nuclear power plant contexts. So that's a lot of time series analysis, doing machinery prognostics, trying to predict when a failure or some maintenance event is going to happen before it happens, using all sorts of machine learning techniques to try and look at using the time series as a data set and making predictions from there. So that environment was very, I think, a fairly typical kind of PhD environment for somebody studying that in the UK around about 2009, 2010. That was when I started that work.
And it's
interesting because at the time we never even referred to the work we were doing as data science. That predates, I think, the boom in the area, like you're describing, the move to create data science as a discipline, having folks in industry and working as part of software teams to try and bring techniques like machine learning towards a software system, and other aspects of statistical practice as well, bringing those towards software systems seems to fall under that bracket of data science. But we didn't even refer to it as data science when I was part of a research team. It was intelligent systems techniques or applied machine learning, or even just data analysis was the term we used at the time. So that was my background. And towards the end of that, I decided I wanted to move towards working in a more product-driven environment. So working for a software team to try and help build better products using the knowledge I had. And since then, it's been I probably learned more since I left academia than what I learned when I was there. I mean, it was a great experience. The 4 years I spent at Strathclyde were superb, but very much my career since then has been trying to take the idea of specifically machine learning, but I suppose other aspects within the data science toolkit and hopefully bring some value to a software product as well, but in the context of delivering software and putting things out towards a product to use in some business case as well.
Yeah, and just as a quick sort of interjection, I thought that was interesting that within your academic publications, for example, one of the obviously you came from that sort of engine anomaly detection, the mechanical type approach. I came directly when we met, directly from the patient monitoring side, and yet, for example, a lot of our citations and papers were on the same people because you had been citing my supervisor
That's right,
and my academic grandfather in that regard, which is, again, one of those things where it's funny how a lot of these techniques revolve around a certain hub. So that connection was there originally.
I think your supervisor was originally working in machinery condition monitoring directly, wasn't he?
Yes. Yeah.
So I do remember. Yeah, you're right. There was definitely citation crossover amongst the kind of the publications we were looking at and contributing to as well.
Mm-hmm.
It's interesting though. I'm not sure. I mean, from a methodological perspective, you can see why there's a confluence between those two. At the end of the day, it's time series you're looking at. I mean, very different physical processes, the human body versus a turbine generator. Those things probably couldn't be more different, but it does seem that there's an interesting aspect to this as well, that fair enough, those domain areas are very different, but the toolkit that you use is very similar, and the way you solve the problems is very similar, which again is something that we're seeing in data science. There's a set of kind of key skills that data scientists will have, and those will apply almost domain independent to a lot of software problems. If you've got experience working with time series, then there will be a lot of time series problems in software teams that you could potentially solve. So it's interesting how there's that overlap in academia as well as seeing that in the real world, so to speak, as well.
Yeah, I think there's good reason why there's such an overlap in, for example, like turbine monitoring and patient monitoring, and the examples are one. And I think this also relates to why we can be very hopeful about a science over data analysis. So for the people who like the term data science as a scientific approach to data analysis, and a scientific and inductive understanding of, data and methodological combinations, which is another definition I like. I think it's just sort of different from the other. I like two definitions and they're fairly orthogonal. So something like a principal components on data science. But there are reasons to understand why these two things overlap so much in the methods, and because one, they are time series, they have a high density of observation. Those observational time series, or those not observations, or like data acquisition. So they're very dense. They have steady state processes. The non-steady state processes they have are typically well understood, or at least essentially they follow certain they follow sort of certain archetypal data anomalies and things like that. And so essentially you can have steady state, and you can have a well quantified steady state, and then deviations from that steady state follow certain archetypes, and then you can do analysis around there. So I think it's one of those things where and obviously there's also a high value in making sure that both those things keep on working, airplane engines in human bodies, or mechanical engines in human bodies. So yeah, I think that's one of the interesting things. But so you made, so you were working in academia. You were, successfully doing work in anomaly detection and data analysis. And as you entered industry, essentially the demands changed for what was required of you.
Yeah, definitely. So I wanted to change what my focus was, mainly because the opportunities were becoming more and more available around about 2014. It will have been towards the end of 2013, and I'd been keeping tabs on basically what had been happening from even just from a recruitment perspective. Opportunities were coming up for folks with our backgrounds, with doctoral level qualifications in the areas of data science more broadly, but statistical practice and time series analysis and all these things. And it was just a very exciting time to then have a look at what options were available to someone who wanted to try something a bit different and maybe go and work for a bigger software team or work for a startup, for example. And that actually is what I ended up doing. I found an opportunity to work for a startup based in London called Music Metric. And the product was basically like a music analytics dashboard that took aggregates of social media and other kind of, I suppose, social network-based metrics, and presented those to folks who were interested in in tracking artists from a like a kind of commercial performance perspective. They also had a really unique data set, and they used some clever polling of the BitTorrent network to get a measurement of how much individual file had been pirated based on its usage on the BitTorrent network. So that was a really interesting data set to have a look at from the perspective of, it gave insight into something in 2014 that was still very prevalent, maybe before the streaming services had such a grip on everybody's use nowadays.
Personally funded by Lars Ulrich of Metallica, no doubt.
Yeah, exactly. And that's a long story, going from way back in the Napster days. But at the time, BitTorrent was the major. I mean, I'm actually not sure if, in terms of peer-to-peer sharing, I presume there still is plenty that goes on. But certainly at the time, that was a huge topic in the music industry. And the engineers had built like an entire process behind the scenes that would, as a product, would poll this network and save the data for kind of insights to be delivered to folks who were interested in this. So the clients we kind of had were like Google and Spotify and A&R agents for individual kind of labels and artists and things like that. So it was a really interesting data set to work with. And the idea was, it wasn't necessarily to find things. This is where the shift was from my experience within academia. It wasn't so much you're not looking for research novelty or to write a paper or to try and take a problem set and think how you're going to uniquely contribute to that area, which is obviously the central part of what we do in academia in many cases. It was just trying to find what are the kind of useful insights and what are the useful potential product developments you can make off the back of that. And we certainly did some kind of researchy type work as well, but that was the biggest change for me. And the change in mindset was looking at the available resources and then looking to deliver business value, I think, rather than looking at the kind of research novelty aspect, which I'd been so used to working in academia as part of my research department. And that's been quite an adjustment, I have to say. Like I certainly, speaking to folks who come from, it's a fairly typical, I suppose, trajectory for people to come on towards data science, as you come from a background where you're working in a research team, you're writing papers and you're contributing to journals, and then to come into industry, it can be a bit of a mindset shift to try and, because you find yourself drawn to like the shiny aspects of really interesting deep questions when there's potentially a lot of much lower hanging fruit that will deliver immediate business value that you have to focus upon. And that was a huge adjustment for me, certainly in the first few years of me moving away from academia towards this more data science environment. And to be honest, the first few years of working, we actually ended up becoming a part of Apple. We were acquired as they looked to spin up Apple Music and the analytics arm behind that. It was still very focused on, I guess, analytics, really. It was still doing a lot of reporting and kind of making sense of the data. And then beyond that, I decided I was more interested in, rather than doing things it's maybe looking at things from a reporting perspective with data science, looking at data sets and trying to make sense of them to communicate insights, or, trying to communicate just the nature of the data to stakeholders who maybe aren't necessarily skilled in that area. I decided I wanted to be more in taking the data and trying to build features as part of software systems. So I went on to be a part of the team at Skyscanner, which is a big travel search engine. And since then, I've worked for a few teams, and the focus has been much more on taking data and trying to take the data and leverage that as an input to the software systems to provide some kind of product value from the data as an asset, rather than doing the kind of reporting part of it.
Yeah. And I guess maybe not to be constantly interjecting the weird little connections here, but there's also the Skyscanner connection between us, where effectively Skyscanner, the Alistair Hahn connection.
I've actually never thought of that. Yeah, that's a very good point. Yeah.
So to make that explicit, I'll let you describe the Skyscanner aspect, but effectively, my doctoral work was meant to be sort of an addition or a furtherance of a previous Oxford doctoral student whose name was Alistair Hahn, who was very entrepreneurial, and effectively he developed an IID method for identifying whether or not a patient was deteriorating. And if you go and look at one of the first two videos in this on this channel, you'll actually see something from like the University of Pittsburgh Medical Center, and It was effectively a prospective study to identify deteriorating patients on a step-down ward and using this IID method. And the task that was handed to me is like, okay, Alistair and some previous people did this work. And now, Glenn, you bring this into sort of the time series, the Bayesian non-parametric approach, and see what further advantage we can get from that. And then the Alistair Hahn connection for you is...
Well, Alistair, when I joined Skyscanner, he was the CTO of the organization. I'm not sure how long he'd been there. It was certainly would have been an extended period. I believe I think he joined Skyscanner as part of an acquisition as well.
Yeah, he was acquired. I believe that he was CEO of a I'm forgetting the name, but I think it's sort of the Z or something. But essentially, he had created his own technology for route mapping and finding ideal prices. And Skyscanner came and just nabbed that. And I think he's working on both those. That at the same time that he's doing his doctorate. So again, he's also a doctoral student of the aforementioned people who were also co-citing my academic grandfather and things like that. So yeah, definitely a multitude of interconnectedness. But anyway, that's just a weird connection. But
yeah, I hadn't really, because I remember reading some of his I definitely remember. I was definitely aware there was a connection, but I maybe wasn't sure it was as strong as that. I believe I knew he'd been either part of a similar group to the one that you were in at Oxford, yep, or it was maybe adjacent to it. But I had no idea the connection was that strong. So that's quite funny. And yeah, more evidence that for folks who are maybe thinking about moving from an academic background towards being maybe more perhaps tech kind of company focused or moving towards industry, there's a kind of strong tradition of folks doing this over the last 10 years plus. So
yeah. But back to what you're talking about. So I thought it was interesting, and I can definitely confirm that in academia you can do a large number of things, and there is obviously a high reward for sort of the technical spectacle of things. Or if you can do something that's very shiny and interesting, it's better if it's more complex and shows how smart you are. That's a great way to do things. They prefer the Bayesian optimization for personalized Gaussian process approaches, as opposed to, for example, a dashboard that would just let you monitor patients across a ward and things like that, especially when you get into the more engineering and machine learning side of things. But in industry, you can get those, as you call them, low-hanging fruits. And I think that that's a pretty common term where they're just saying, like, okay, for a data scientist, given that we're paying you so much, why don't you earn your salary? And what are the things that you can do? And there's a bit where effectively a lot of the data exploration phase for a data scientist is actually close to a deliverable product for a team. So effectively what you're doing just to explore the data before you build models could more or less be a useful product to the rest of your team. And the advantages of that I can see are, one, you don't have to create these more formalized statistical inferences. You don't have to create some formalized predictive models. And I think the formalization of those processes and all the extra work that has to go into formalizing them and making them reliable is the vast majority of the effort. Whereas a lot of these more visualizable, sort of where if you can basically create views of data streaming in and do some anomaly detection, things like that, where you can still use statistics to flag important data, but just providing that view in is a very useful thing. But obviously that's not the only thing that's there. So maybe the next thing is to say, well, what if you do want to do the fancy machine learning and start delivering that? Is that the next step? Or did we miss something?
I think so. I think still there has to be a strong tie towards, we talk about maybe business value, but there being a problem to solve. So, certainly my experience in academia was when you're looking to apply a set of techniques, be it a machine learning approach or otherwise some other statistical technique, for example, solving the problem was good. But I think, like you're saying, the kind of technical spectacle was also part of the process as well. And admittedly, yes, building a machine learning model to solve a business problem or to improve a product, for example, that process will be much more complicated and take a lot more technical work potentially than doing maybe more straightforward data explorations and stuff like that. But at the same time, I still think there has to be a very strong view of what it is we're trying to achieve at the end of the day. I've certainly been guilty of this in the past when I've, trying to earn my stripes as somebody who was maybe more product focused, and trying to contribute to work as part of a team where, you've got a problem, and I've tried not to, as part of the team, we've tried not to solve it necessarily in the minimum viable solution to the problem to begin with, and iterating from there. It might be a shiny aspect of the problem space, meant that we focused on a really technical detail first, or we tried the more complicated approach to address the problem before we tried maybe more simple things. And I think from experience, it's definitely where I personally had more success is when you've taken a much more incremental approach towards moving something that's perhaps proof of concept towards a production system, for example. So admittedly, while these things can be really complicated, I think still having like a strong view of what the minimum, like I was saying, what the minimum viable solution would be to get that into some delivery mode, be it serving predictions if it's a machine learning model as part of a production platform, or even if it's a piece of technical analysis that's been done ad hoc previously, automating that process or making it more automatable and kind of reliable and robust. These are all useful things to do, especially as people get more and more buy-in into the kind of work you're doing as a data scientist and the contributions that you're making. Because although sometimes those might not be the types of things that we will have done in academia, they're undoubtedly providing like a monotonic improvement to the state of play in whatever business it is you're contributing to. I'm not sure if that answers your question or not.
Yeah, no, I think it does. And maybe it would help, for example, should we just maybe use a quick toy example that is probably pretty close to things that both of us have done, where we both have an academic version of it and sort of a more industrial production version of it. So, for example, say that you're trying to monitor a number of entities where, say you have a number of, I'm trying to decide how explicit I'm going to go on this, but essentially, say you have essentially a number of sensors, for example, and each of those sensor is of a unique value. So each of those sensor might be a customer, and that customer is generating a series of values. I'm not saying it's like a super continuous time series, but they have multiple values over time. And so effectively what you might be doing in the academic setting is saying, okay, when we try to detect these anomalous, which customers are anomalous, what we first might do is say, okay, well, let's develop a customer specific distribution for each of those. So essentially we go from having a number of data points to now we have a number of distributions, one for each customer. Mm-hmm. And then that brings up the new technical question. Well, we're calculating the distribution, but how do we know our distribution is good? Because obviously we're automating that statistical inference process. And so we say, okay, well, how do we regularize, or how do we improve that so that it's more precise and a better descriptor, such that we have this down the line view of detecting anomalies? And so that might bring in the factors like, well, maybe we want to put in Bayesian priors, and we can put in some priors on that. And you can see where this is starting to go. It's like, but then again, what about other features? So that you might have for these. So for example, in addition to the raw data itself, you might have extra features for this customer. For example, like their customer size, how many employees they have. So effectively now we're doing two things. We're turning this into more of a regression type model, or some broadly regressional type model. And the moment it's nonlinear, it's like, well, which nonlinear model do you want to use? Do we want to use a hierarchical model, or do we want to maybe use a Gaussian process so that we can just sort of plop density where we need to? And you can start seeing that it's like, well, okay, say we're going to use this regressional model. What's the length scale of the effect on the customer side? So how rapidly will these change? And are customers with 10, do they change to the same amount, or once you get super big, does the rapidity of change as well? So you can see that, and those are very interesting technical questions. Yeah. Like that's the stuff that I love to do. But the fact is, each of those steps adds and adds and adds. And yeah, you can look shiny and smart by doing those things. But the question is, for each of those, you need to create a formalized inference step, and you need to basically curate the data in certain ways and make sure that it's very well controlled. Whereas the other option, On the other side is you create a dashboard and you literally just plot that data and give each person a little box, and you can just look at the distribution. And if you want, then you just plot it with respect to this other feature. So effectively, you're just visualizing the effect of the feature. You make a 3D plot, and it pretty much shows everything you'd want. And that doesn't require any of the formalization process that you would for the fancy machine learning or data science work that we all love and sort of really like to see because it feels good in our guts. Is that an example where effectively on one you can keep pushing that and add technical complexity, which it is real technical complexity. It's not like you're making up work, but it's
absolutely yeah. I mean that's a great example. I think the important thing to note as well, all the deeper technical challenges that you talk about, all the different ways that we can slice a problem up, like you're given in your example there, those things potentially are really useful things to do as well. You know, like the fractal of stuff, while it is like a bit of an attractor, like people who are maybe more technically inclined to go and navigate that fractal, or at least try to, well, it's not to say that those things aren't useful, because very many of them will be. I think it's just in the hierarchy of needs for a given business problem, there's going to be something like just the visualization that can be done that will then, it just immediately provides value there's no barrier to or it doesn't need to be unlocked by product of this much more technically difficult set of steps that you'd have to take to look at the more intricate aspects of some of the techniques you were referring to there. I think the important thing to remember is, because sometimes people seem quite defeated by this. They think, well, you know, I really want to do all this really fun work. Like, I really want to look at the details of how we take a given method and we dig into the kind of weeds of it and look at the potential optimization techniques we can use, or maybe we spend a lot of time in the kind of model selection world and we try out a new methodology for, I don't know, like some kind of machine learning method. Those things can be really useful. I think it's kind of like being pragmatic about how you ensure that the delivery of the output from like a data science process, and I talk about that when I say the data science process, I mean like the output from the data science team. You have to just being pragmatic that has to be it's a part of the decision making process behind which route you take as well. But certainly, I mean, there's so many problems within all sorts of domains where that kind of technical complexity is not necessarily even like a shiny thing to go and look at and kind of satiate our curiosity. Sometimes those things are barriers to providing a solution. So there will be plenty of scenarios where you'll be dealing with technically very difficult data problems that will require that level of rigor. I think though it's just first of all identifying those well as part of the process of your investigations is a challenge in the first place. But also, you know, like in the example you gave there, just doing some visualization and communicating the challenge of the problem and maybe giving some incremental benefit to the team more widely is definitely something that I think is a much more kind of like repeatable process to take when you're looking at these kinds of problems. And very often what will happen is it might just be, you know, the exploration part is good enough for whatever people are trying to solve in the business more widely. But at the same time, that's not the end of the story. You know, that might turn into something that's then, okay, we have some data exploration process that a data scientist has run here. You know, how do we look at this and make it more robust, and how do we automate this so it's not having to be done ad hoc each time, or what's the potential deeper questions that this analysis opens up as well? You know, is there other business led kind of questions that we can start to ask based off of that that approach we've taken that maybe wasn't technology driven, but it was certainly problem driven. And I often find from my experiences, it opens up more questions as well. What you'll end up, there'll be more interesting questions underneath that first layer that then become available because you've had this to and fro conversation between the data science team and maybe folks who aren't data science specialists, who you're maybe reporting back to, kind of stakeholders in the business more widely. And then it gets really interesting because there's an enablement and kind of like conversation that happens where you have something that previously wasn't investigated because either the data science team wasn't there, maybe the expertise wasn't available to begin to visualize, even if something as simple as visualizing the data to answer at least the first step of a question. And then maybe if it's a product team you're working with, they then, off the back of that value that's been delivered to them, they go, oh, this is really cool and really neat. We can see X, Y, and Z. So what about questions A, B, and C off the back of the analysis that we've done? And it becomes like a kind of virtuous loop where some really interesting questions can get answered based off of that process working really well. Which I think that kind of does get lost if you try and step back and just try and, well, in fact, not step back, but shoot in for the really technically difficult solution to begin with.
Yeah. So also just to double down on this point, because I think this is important, and so again, there are necessary fundamental technical challenges when you're trying to solve some of these hard problems, and so obviously neither of us are dismissing that. However, I guess what one of the things we're saying is that prior to solving a lot of those really like dug-in technical problems, when you're trying to really add value to these, for example, predictive models, in the process of creating those, there's a large amount of, the reason they're difficult is there's a large amount of formalized logic in those. There's rigorous logic where, just you can't just tell a predictive algorithm to perform well. You need to tell it how to perform well. You need to give the data such that it will perform well, things like that. And so effectively, and those are extremely formal. They have first order problems. Those first order problems create second order problems and third order problems and things like that. And you have to go down the line and knock out each of those. So it's not just saying, just create a model. What you're saying is you create a model, and then maybe you need the model that supports the model, and then you need the data cleaning process that supports the model that supports that model. And so effectively, there's this big root system underneath each little plant that you see. And so no one's denying those. And the fact is we love doing those things. But at the same time, those are extremely time consuming, at least with current technology. And in the process of doing that, you're going to be doing a lot of visual inspection and a lot of other quality work that you could also be immediately deploying to great advantage to the rest of your team and to your company. So whereas one of these things essentially takes a long time, and it's only once it's come to fruition, these complex data science projects, it's only once it comes to fruition that the value is delivered. Some of these other things, like, for example, visualization, dashboarding, stuff like that, which, how many billion-dollar dashboarding companies are there out there? Like more than I have fingers on my hand. And in fact, that goes to show the value of it. And I also, by the way, I'm only a 5-fingered man. So Inigo Montoya, don't worry about that one. But the value in that also, as you brought up, starts percolating some other questions beyond just the ones that the data scientist brings up a priori. And so that's, I think, one of the benefits of these things, where once you bring up the dashboarding, and so you're sort of things say, don't worry, the interesting data science problems will come.
100%. Yeah. I think that one point that's really important as well that sometimes gets forgotten is that, like, this stuff, when you're looking at things from a real technical depth, if for example, we went for a really specific, highly technical, like maybe even esoteric approach to solving a problem that took a lot of work to begin with, let's say 6 weeks or more worth of development work with a real research focus on trying to solve a problem, like with our hypothesis as to how we would solve the problem. And maybe the problem's like a really high value business problem. Maybe this would solve the product. Maybe it's delivering something at like 1x, and then this way of solving the problem, if we got it right, would make it 10x, and like it would change the landscape of how these problems are being solved. One thing that doesn't really get spoke about is that stuff in data science, there's a real uncertainty as to whether anything's going to work before you get into the weeds. A lot of the time, there's a real, I say non-zero, there's a pretty high chance sometimes that no matter what research work we do to try and, limitations on the data, limitations on the methodologies that we're going to be able to employ within the confines of the resources that we have, even limitations on the skill set of the team that are working on it, mean that some things aren't necessarily possible, and that might not even be obvious until way into the process. It might be weeks and weeks and weeks before we've gathered enough information to then say, okay, this is too hard, we can't do this. And that, see, going back to the point you made about agile software that you're talking about in the Q&A, that's a real challenge when you try and integrate data science into agile methodologies, is because if you're looking at things like building sprints and working in Scrum, a lot of the real valuable aspects of of being able to plan and coordinate software development using those kinds of tools is by providing at least benchmark estimates as to how, process, task A, B, and C are going to take, how long that will take a team of 5 engineers to work on. Now, I'm not saying that the software engineers have got all this sorted. Like, software estimation is notoriously difficult to do, but on that kind of like bed of sand, data science estimation is even more difficult to do because of the inherent uncertainty in the processes that we go through to solve the problems. Like building an API can take longer than expected because of unforeseen product requirements, but building like a machine learning model to sit inside that API can take even longer because we're not even sure we have the resources to build everything in the first place from a data perspective or expertise perspective. Whereas building an API is kind of, we've been doing this for a long time now. We've got ways of doing that that we understand how it's done. So it makes it really, that's another reason why we shouldn't necessarily we should be biased away from the more complicated kind of approaches up front, because we don't even know necessarily if taking a really strong hypothesis about how we'll solve a problem with a really specific, detailed, and technically challenging methodology will actually work in the first place.
Yeah, no, that is interesting. So I guess there's a few ways that this can break down. And I think it bears reiteration that effectively you can do a lot of work on a data science project and it literally comes to nothing. And the problem with that is obviously the resources are wasted. At most you might be able to say, well, we now have identified that this comes to nothing, and that's a problem, and therefore we're going to add more. We're going to throw more good money after the bad to build what would be needed to make this work. And so some of the challenges are like, because I don't think people always appreciate this, where there might be a fundamental disconnect between the data you have and the information you need.
Yes.
And so like if you're trying to use that predictively, if there's a fundamental disconnect between what you have as your predictors, your X's, and what you're trying to predict, your Y. And that's, it's not just whether or not it exists, but whether it's strong enough to be worth your time and to be low variance enough and things like that, such that you can do something with it. So, and I think that it's, you can't tell that deductively. It's an inductive process. It's also prospective as well. It's highly prospective. And when you compare that to something like, well, you deliver a dashboard that's much quicker, and is also going to generate new hypotheses. So the other thing that it does is this brings up, instead of basically trying to say, I'm going to be the one processor on hypothesis generation, you're essentially bringing this, you're parallelizing the capacity to generate hypotheses, which then means that effectively they can bring up things. And one of the, are you satisfied with that? Because if so, then I'll move over to the next bit, sort of the good news, if you will, where you can
I think that's a good summary as to kind of like where the challenges are for dealing with like these kinds of projects, really.
Mm-hmm. And also they can have immense mission creep. So the risk of mission creep is in all of these things.
I mean, 100% mission creep is, I think, especially in areas where there's a lot of, everybody who works in industry will have had an experience of trying to, like the value of doing this kind of work doesn't need to be communicated to a lot of savvy, let's say, project or product managers or product owners. But the limitations as to what can be done definitely needs to be explained. So you often get very excitable product owners who work in large software teams who would be like, let's apply this really kind of like vogue technique to this particular problem, and then this will solve all the product problems that we have. And it's the understanding that needs to be kind of hammered home that it's just really difficult to do a lot of the time, and kind of managing expectations on that front is often like a really important part of the kind of collaborative process between people who are in the data science and machine learning side and folks who are from larger parts of the business as well.
Yeah. And so I guess, because obviously we like to have good news in here, like the thing is like, you can actually get to the cool technical work that you want to do. This isn't saying, oh, don't do cool technical work. I think we've been clear enough of that already. Someone would have to be like fairly dedicated to ignoring what we're saying to say that we don't want to do that cool technical work. The challenge is like, well, how can you get to that cool technical work? And essentially doing these more like incremental low tier projects to begin with, essentially what it can allow you to do is parallelize. So just consider a dashboard as opposed to a predictive model. Now you've parallelized the hypothesis generation process. So now instead of you being the only person who generates hypotheses, or you and your manager, it's now a large number of people who are looking at that dashboard, the software engineers, maybe some product managers, or project owners and things like that, and maybe even customers on some level. And so effectively, you now have a range of problems because the hypotheses are being generated in parallel. You now have a range of problems that you're allowed to, from which you can select. And I think that one of the places where a natural place to build off from, for example, visualization, is then you try to deliver basic value at volume. So, and that immediately can become a very data analysis heavy issue. So essentially people can say, oh yeah, this is a cool dashboard, and I'm seeing these points that don't quite make sense. Which data points are these? How do I highlight them? Can you tell me which these are in advance? And so it's like, well, boom, now you've gone from something saying, well, you don't just say, well, just hover your mouse on it. It's impliedly, it'll tell you which data point it is, because obviously that's not quite it. But like now when people say, this is interesting, can you bring this to my attention? Prospectively, you've now created a new predictive problem. You've had it validated that people need that. So essentially people are saying this is of interest. And so then maybe the next increment is saying, okay, let me try a fairly simple anomaly detection method, et cetera, to start flagging these. Okay. Is that an okay path forward? What are your other options?
Well, I think, yeah, I mean, in the case if the product that we're delivering is a dashboard, like you're kind of already hinting at the fact that if that's for internal stakeholders, that's great, because it means that you're going to free up this constant ad hoc reporting function that data science and data adjacent teams will often end up having to do. Because there's a lot of talk amongst teams and companies more broadly about being data enabled or data driven, or using data and evidential kind of reasoning behind making decisions from a business and product perspective. But when you give people the data just without necessarily the context and the explanation around it, that's great, and that's a huge value add, I think, for a lot of scenarios. But it becomes the next stage of the problem is how that the ongoing kind of support and kind of business as usual, I suppose, parsing and understanding of the processes that are being now instrumented properly via dashboard, like how that is done by folks who maybe aren't necessarily data experts, is really challenging. So an example you gave, so someone will be like, what are these? These don't align up with, so for example, let's say it's a particular set of data points on like a time series, and they'll say this doesn't align with what I would expect to see at this time, or there's some other explanation that we need to have given to reason about this part of the data that's being visualized. And you might decide, yeah, that's a good idea. Maybe we should look at some kind of anomaly detection process to either flag these parts or to remove them entirely. And that's certainly one way of trying to approach that problem. But now what you're doing now is like looking at, you're turning like what originally was like I suppose just an instrumentation and kind of dashboarding problem into now is becoming like a proper data product. And how you build that anomaly detection process, which by the way can often be like, not just in dashboarding, will often be like a hugely important part of like a product more broadly. Anomaly detection systems have become central parts of a lot of the products that I've been able to contribute to. That it's not necessarily in some kind of like time series output that it's flagging it. It will be some set of scenarios, for example, that we decide the product that we're developing either has to be aware of or has to avoid, or these cases have to be flagged up from like an instrumentation perspective, not customer facing, but operationally facing, like understanding the dynamic scenarios that software can end up in using anomaly detection is like a really, I wouldn't say it's a repeatable pattern because it's so challenging and domain specific in certain areas, but it's certainly like a repeated kind of value add from data scientists who'll be working as part of like of software systems. On the dashboarding front, you have to make sure that the anomaly detection scenario and the anomaly detection product that you're building on top of the dashboards is going to solve the problem, because if an individual product manager, like a stakeholder in your team from the company more widely, says, I don't understand these points, I mean, those may be anomalies from I suppose, looking at the context that data has been parsed in by a non-stakeholder, but to then spend the effort building a product on top of that to then deal with that the individual whim of that one stakeholder, there has to be like a real understanding as to what it is we're trying to achieve by doing that. And if it's a case of, this is just, if there's loads of examples of where, let's say we have a dashboard monitoring some kind of process that's of business like importance to stakeholders outside the data team, shall we say. And we say, there's a lot of noise in here, there's no value add to it, and there's no scenarios that we're interested in presenting this data in, like that would be of any business value. Let's build an anomaly detector and that will improve things. But often those cases that might be of no interest or discardable for one stakeholder could be of interest to others. So it's again trying to get that. I think the answer is it depends on whether that's a useful thing, which is never a useful answer, but it covers things so broadly a lot of the time.
Yeah, I mean, I think
sure that there's an understanding as to what you're trying to deliver to add that kind of extra kind of feature on top of just the communication of the data as well.
Yeah, I mean, I think the key to that, though, is that the best result is to have some type of like NLP model on top of that, such that you monitor all interactions with the stakeholders, and then you have a predictive model that tells whether or not they'll appreciate your anomaly detection method.
So doing sentiment analysis of your coworkers?
Yeah, something like that. Just and I think that's really where people need to be placing their time these days. I mean, if you're worth anything, otherwise, So I think that's helpful. So this is helpful in the sense that if we recognize that the vast majority of people in the data analysis field do appreciate, and I know we'll keep reiterating this, but I like to keep the train of thought, is that we want to do a lot of these fancy and interesting things. The data analysis is typically what we love. And so that means that like sort of on the first step, we tend to go off on this one branch that might say that we'll just turn everything into a research project. However, if you can scale it back, parallelize the hypotheses so that you're not the only person, then essentially you have a large number of things, different projects from which you can choose. And then you can provide incremental value on those. And that those more frequently than not will lead to the same type of interesting problems, but now we're a bit better latched onto one that's probably more important, one that's already more tractable because you've already put in the data exploration phase and things like that. So now let's say, okay, we essentially have these, we now have a predictive model that we want. And it's time people have assessed the value of this. And now it's time to essentially try to start like fusing this into the software solutions, treating this like a software solution. And this is the bit where you have extensive experience with this. My experience is a bit more on the toy level, where effectively the farthest I've gotten with most of these things is essentially embedded analytics in the dashboard, and deploying those to make sure that they're good enough. But as far as saying things like, okay, rigorously, how do I test that these things work in all scenarios? How do I deal with the different software outputs, things like that? Beyond basic, creating little distributions, testing input versus output type of things in scenarios like that. A little bit of model tracking, like if, for example, just seeing if in different segments over time, your model's having drift or there's feature drift or there's drift like that. And of course, I get to create cool dashboards like that and play around with the machine learning bits on that. But formally, for someone who's actually good at it, unlike myself, what is the process in that? Because I think that's sort of where you're trying to really spearhead.
Definitely. I mean, first of all, when you describe my experience as this is extensive, I mean, it's definitely been my focus for the last good number of years now. But one of the most exciting parts of this aspect of the kind of data science development process and software more generally is that this is all so new, and there's so much still to be defined from certainly from a best practices perspective. Now, there's a few best in class companies that certainly have processes that I've actually largely been kind of, say for a few notable examples, that they're kind of largely obfuscated from the discipline more broadly. So the ones that jump out are these kind of large, kind of FANG companies. So Google's the kind of canonical example for an organization that's able to productionize kind of machine learning at scale and doing that while delivering kind of product value. And there's obviously other teams like Apple and Uber and Facebook who were doing similar things as well. And there'll be more domain-specific examples, but to me, those are the teams that kind of have the most kind of operational experience behind doing this. But there's not as much kind of broad agreement across the industry as to how, even just the question as to how we move from that kind of proof of concept stage where we have a model or a feature or something that's been analyzed and experimented upon and developed in collaboration with stakeholders in the organization, and there's a clear product need for it. But even just the movement of that towards a production scenario is something that there's a flurry of activity at the minute, and has been for the last, I would say, 18 months to 2 years, from like a kind of software practice perspective. And I'm not really sure what the reason for that is. I think maybe the prevalence of tools from like a compute perspective and from a data availability perspective they've certainly reached there seems to have been some kind of like action potential we've got past over the last 5 years, where things that were previously exceptionally difficult are now becoming, from like a data engineering perspective, are now becoming much more tractable and much more commoditized. So historically, so if you give a specific technological example, there's a tool that I've been using on and off for the previous, since 2014, so I don't know how many years that is, so it's 7 years, called Spark, which many data scientists who are working in teams will be familiar with. Mm-hmm. When I began using that, it's been an Apache project for I think since the outset, but it was very difficult to use to begin with. It's something that took a lot of like development of kind of very specific skills and understanding to make the tool work, to do in-memory data shaping and analysis and some machine learning if you were interested in that aspect of it. So back then there was a lot of kind of investment to make that work, and then the operational stuff behind the scenes to make it part of your software stack was very. You had to put a lot of investment and time into that as well, with multiple kind of like software experts contributing to it. Not just the actual data science output of that becomes maybe a data pipeline thing, but in the running of the cluster behind the scenes to make sure that works correctly and is available for data scientists to use as a tool. But nowadays, because of tools like Databricks, this is now a managed service that you pay for and you get access to, as your team will get given the keys basically to do all the cluster computing that you would want. So this has meant that teams are able to get spun up doing this kind of stuff that historically, even as little as 5 years ago, was really difficult to orchestrate, but is now much more accessible and can be spun up a lot more quickly than it previously had. So that's one explanation as to why this is becoming more of a kind of topic of conversation now that we've got the compute and the process to deliver these data science or machine learning assets to the point where we want to put them in our products more widely. It's become much more a commoditized thing that smaller teams can do that. But the challenge with software is always, it's not necessarily making the thing work in the first instance. It's not a case of proving that your approach works. And this also applies to just traditional software as well, not necessarily data science focused stuff. But it's what happens when you put that out into the production system and how that piece of software exists from a continuous development process. There's a whole area where software developers will talk in depth called continuous integration. Basically, practices for making sure that if there's multiple developers working on the same project, that those contributions can live with each other from like just to make sure things don't break perspective, but then also to make sure quality remains high as well. Taking like something that's as simple as like a change to an API is not as a non-trivial thing to orchestrate from the actual software delivery perspective. And it makes sense that doing this for data science is really difficult too. So now there's a whole host of startups and companies who are looking at, the kind of broad term for it is looking at, they refer to it as machine learning operations. So now we've got the data science value, we've got the stakeholder buy-in, our model works, great. What next? We move it towards production, and it's not just an overnight thing that we decide, okay, well, to Monday morning, we'll just drag and drop the model file to this new directory somewhere, and then we deliver predictions, and that's the end of the story. Like, this ongoing process is like it's a new kind of, in many ways, it's a new kind of software that we're having to learn how to operationally support and develop upon and kind of work with as a component in production systems. And it's almost every day there's people writing new materials about how they are trying to approach the problem, how they think approach Y is better than approach X. So there's a huge flurry of activity in this area. So to describe it as my experience has been extensive, I've certainly been thinking about this a long time, but like this is all very new to almost everybody, except those who've been delivering kind of high scale machine learning at the scale of a Google or one of those large companies for the past however many years they've been doing that. So to be honest, like there's two sides of the coin here, where it's really challenging, but it's also very exciting to think about this in any kind of depth. I think the main thing that I try and proceed with forward is, at the end of the day, if you're delivering something that's going to be product focused and is working in a production system, at the end of the day, it's all software, and there's practices that we have for software that isn't relying on empirical processes to develop, like machine learning models, for example, are. And we can begin to look at how we do this for conventional software and try and apply it to those more empirically defined pieces that are so kind of characteristic of the data science development process. And that, just saying that is not easy. Like, this stuff is really difficult to do. Mm-hmm. It's just it's almost like, it's not like the kind of addendum to the data science process where, it's like there's a single step that we then see, and then we put it in production and everything lived happily ever after. Like, in my view, I think this is where almost a whole new discipline is going to develop over the next 5 to 10 years. And it's only now we're starting to see kind of people looking at this in earnest. And there's loads of really, really interesting and cool technologies that people are building, purpose-built for this kind of stuff, from model orchestration to serving to instrumenting. Like you were mentioning there, there was, I think, Glenn, you mentioned like 5 or 6 different things there, from like a serving and instrumentation and testing perspective. And these things are like, these all make intuitive sense for us to talk about from a quality perspective, but the tooling just now doesn't really exist for many of them, which is scary, but it's also really exciting as well.
One of the and maybe tell me if this is like an apt, one, analysis, and two, whether it's a worthy comparison. So whether it's both accurate and or useful. And so I view software development as essentially a deductive intellectual process, where effectively like A follows from B, B follows from C. And, if you make the incorrect assumptions about, for example, what type of data comes in or something like that, or how people might click or interact with it, you will get errors in your software. However, it is fundamentally a deductive process, where if you can get each layer in turn working as you expect, the outcome will be precisely as you expect. And that typically, when you have errors in these type of software developments, it is because you have essentially a faulty assumption or a misunderstanding about the scope of what you might be asking at any given step. And so that's why I view software development as a deductive process. In contrast, I view data science and machine learning and statistics as it's deductive, inductive, and abductive in the research and development phase. And then the moment you pop it out there, it's hugely inductive. So effectively, you have these different modes of thinking. By inductive, I mean, like you said, yes, I know that it works under these scenarios. And now I'm going to suspect that it works under the rest of them, or whatever else I throw at it. And so effectively, part of the challenge here is that the scope of error has increased greatly, and beyond just what you could control in a research setting, because obviously you're deploying these. There's a difference between, for example, when I was a statistician in the Oxford hospital system, saying, here's the model, here's what I found, here are my results, here's all this extra bit, handed off to a lab scientist or clinician, and they used it. Very different from saying, like, okay, here's my thing, time to just launch this into space. Yeah. Or alternatively, I'm going to put this on your space satellite, and it's just going to do its thing. Don't worry about it. And so I think those are two different processes, and I think it is very helpful for people to make the distinction about why precisely these things are breaking down.
I think that is a very useful way of describing the contrast between the two components that are now. I think the thing is, these components are having to now live together. Like, I think this is the kind of key point, is we've now got these two kinds of components that now live in the same world. And I would actually say as well, if we go back to just like the traditional software stuff, it being deductive, that makes it seem very, I mean, when you look at testing a software system at the smallest kind of unit of a like a function, or just the smallest kind of like logical way of analyzing a piece of the system, it seems almost trivial to folk who haven't necessarily worked as part of larger systems. And from a development perspective, yes, everything's very crisp. From like an inferential perspective, we have to, if you put input A and you're always going to get output B. So in that sense, it's very, very deductive. But the challenge is when the kind of combinatorical like explosion of stuff happens when you begin putting these bits together, and you get multiple players who are acting on the system at any one time with their own requirements from a development perspective. They have their own biases from a development and design perspective. I mean, in many ways, a software system is kind of like a huge living document of prepositions and then outputs, and to then 100% is deductive, but it becomes, I wouldn't say quite chaotic, but it becomes really difficult to keep a track of what's happening when those deductions are being altered and tested in different ways, hundreds of thousands of times, depending on obviously the complexity of the software that you're developing, which is why testing becomes so important for even just conventional software. It's something that it makes our assumptions about the component parts and the system as a whole, it makes those clear, and they're tested rigorously as part of a continual cycle that ensures that we don't introduce problems when we make a change. Which makes for anyone who's from the software background, this stuff will all be very familiar. There's debate about how central testing should be to software practice, because obviously it has some effect on the velocity that you're able to write code at if you're having to write tests at the same time. And there's a lot of cargo cult stuff where people say this is the way to do testing, or this is the way to not do testing, or we don't need tests at all, we'll just do it. But broadly, I think people would agree from a software background that testing is at least useful in a wide variety of cases. But the very interesting thing to me is that if you take that purely deductive set of components that are complicated in the way they're intertwined and codependent, and then you are testing those to make sure that things are okay from like a base case perspective, and then we're adding this inductively designed and derived component into the mix there, that just adds so much more complexity to the area, which again is scary, but it's also is very interesting from like a kind of challenging technical perspective to try and see how we make these two components play nice together. Because often when we take like our predictive models, say, that can be deployed as like, a user comes along and they ask the model in some format for a prediction about their input, and we get the input back. I mean, that's fairly ring-fenced and independent from, let's say, the API components that serve the infrastructure around about that artifact. But increasingly what's happening is the inductively designed data science, machine learning components are becoming parts of the pipelines of software more broadly. And when your output from like a machine learning model is an input to another potentially very complicated piece of software, then goes away based on that output to kind of like come to some other conclusion to provide some other action to another software system. And you scale that up across, I mean, nowadays when you look at software systems at the top level of an architecture, if you look at things like microservice architectures, these are very complicated systems at the highest level. The potential for uncertainty to be introduced to these systems is enormous, and that's just the integration part of that. Like that's not even thinking about all the stuff we've just talked about for the last hour from the perspective of the uncertainty behind developing the component from a data science perspective in the first place. So there's a real kind of coming together of these two cultures, I think. That there's a lot of work to try and to make these two things play nice, because truly, I mean, it's really exciting what we can potentially do and what we're doing already with data science and in production. I mean, there's so many products that, I mean, to somebody who's not necessarily data literate, some of this stuff seems like magic. The idea that you can have something as simple as like a takeaway menu for a local, or an Indian takeaway that wasn't necessarily on your radar before, recommended to you based on like your preferences of food orders over the last 6 months. Like that seems, to somebody who doesn't understand software and data, that seems like it's unthinkable that would happen. Something as benign as that would happen 10 years ago. So the outputs of this, I mean, obviously that's before we even get into the topics of like the areas that you've obviously been working in from medical perspective. Some of the stuff that we can do with this is going to have a huge impact, and is already having a huge impact on the world, kind of writ large. But it's making sure that we do it the right way, and we don't introduce all sorts of crazy uncertainties into our already pretty difficult to track software systems more broadly.
Yeah. So maybe just to summarize this last bit. So obviously we've described the software development we've described software development as a deductive process. However, that does not mean that it's straightforward or unchallenging or simple. Because it's essentially you can have a large number of simple mechanisms, and when you put them all together with all their own assumptions, then immediately can become an extremely complex problem. So sort of like you can have a system, and depending on what your initialization points are and things like that, you can immediately have something that spins off into something very strange. And also some of the challenges of that when you have to bring multiple deductive systems together. If there is a conflict or a contradiction between any one of those components, that might only arise in an extremely rare case, one that you might not, for example, think about with all the other work that you have to do and things like that. So it's not to call these systems uncomplex. They're highly complex. They're highly complex in a certain way. And perhaps they're so highly complex in a specific way that the nature of that system is now effectively, on some level, somewhat of an inductive system, and things like that. So, there's a lot there. It's sort of like, those little things where you drop a ball and hits one peg and then the next peg and the next peg. Each of those individually is like a small piece, and it's a very straightforward, simple process. But when you put them together, you can imagine the variety that can be created, and enumerating those across multiple dimensions, across the variety of each of those dimensions is quite difficult.
Well, one interesting point, actually, I've never looked into this, but I might have a look at this evening after this call. But whether anyone studied software as a complex system from like the formal definition of complex systems, because it seems to me, as a layman in that aspect of complex science or complexity science, that it seems like that would be the case. And the point we're getting to is that by adding these new components into it, the complexity is even greater potentially as well.
I think that would be an interesting, and actually maybe that's a good place to stop for today. Because basically, you have been working on how to deal with these systems, and I've been hoping to have a few conversations with you because obviously there's a lot to unpack here. But maybe for a future conversation, what we should cover is, one, we should answer this question: is this available as a complex system? And two, regardless of that answer, what are the different types of testing and things that we can do to start trying to come to grips with these types of systems? So, obviously there's a lot of it with like the regression testing, the unit testing, and maybe once people have some time to digest this conversation, we can come back and talk about these other ways. And we'll do some recap and things like that. But does that seem like a good place to stop for the day?
Yeah, that sounds great.
Cool. Yeah. So I really look forward to our next conversation. And the conversation after that, because obviously there's a lot to uncover. So, Jason, thanks so much for your time today.
Thanks, Glenn. Cheers.
Hey, guys, it's Glenn. Thanks for your time today. I hope you liked today's episode. If you did, please consider smashing that like button. It's the single, simplest, fastest way to make sure that YouTube shows this video to more people. If you really want to go crazy, consider subscribing or going to our website and joining the mail list. If you want to go totally crazy beyond that, forward this to a friend or colleague who you think might enjoy this too. We're a small channel and every bit helps. Our next episode will be coming out next week, so in the meantime, feel free to look around the channel and see other videos that might be of interest. As a quick disclaimer, the views expressed on the show do not represent anything other than the people saying those words, views, etc. like that. It doesn't mean anything about their employers or their employers' views or some thing about their employers or their neighbor's cat or anyone else not saying the words. And in fact, given that people tend to change their views when they're thoughtful enough, it might not even represent the views of the speaker by the time you're hearing the episode. So definitely come back and see if they've changed their views at a later date. They also don't represent the views of our sponsors. Thank you to our sponsors. You can check them out on our website.